and welcome to part 5 of this course on symmetric computation. So, to sum up very briefly what we've done so far, we've looked at what you might call a model of computation and shown that it has equivalent characterizations in many different forms: as a machine model in the form of relational machines, as a logic in the form of fixed point logic with counting, or more generally counting logics, as a circuit model of symmetric circuits, or polynomial size symmetric circuits, if you will, and as a linear programming model. I mean, you can think of that as another model of computation, that of symmetric linear programs. So very different ways of defining a class of structures, at the core of which is a notion of symmetry or invariance, but the key idea being that you work computationally with abstract structures rather than with string representations of structures. So we've explored the relationship between these models and their equivalences and how we can establish them. And at the same time, we've established the limitations of the model and shown that there are certain things that the model simply cannot do, which are computationally feasible, right? Like our concrete example was the Cipher-Ullmann graphs, but from this it follows that solving systems of linear equations over finite fields, or for example, the XOR SAT problem, are not doable in this logic, or in this formalism, in this model, if you will. So what we're going to look at in this lecture in 3 parts is, first of all, some applications of this, in the sense that there are natural classes of algorithms which can translate into this model. They are naturally symmetric. And what we are able to then show is that for those algorithms, certain things are not solvable by those algorithmic methods, and this gives us real lower bounds for real concrete problems, and we look at that particularly in the context of constraint satisfaction and approximation algorithms. And then in the last part, we'll look at some extensions of these ideas. So people have proposed ways of going beyond the power of fixed point logic with counting, while staying within polynomial time and still having certain kinds of symmetry invariance. And we'll look at a couple of those things along those lines. So one of the key notions we've defined as we've gone along is that we can take any class of structures, for example, a class of graphs, and associate with it a function, which we call the counting width of the function, which gives for any n the least value k, such that some formula of ck defines exactly the structures in C with at most n elements. Right? Is the small, which is basically the same thing as the smallest value of k, such that the class C restricted to structures with at most n elements is invariant under the equivalence relation associated with CK. This is at most n, because you can show that if you restrict yourself to n elements, then, well, n equivalence, Cn equivalence, is the same as isomorphism on structures with at most n elements, and you can always take any definable class and express it by a single formula. Okay. For those classes definable in FPC, and more generally with the non-uniform versions we've looked at, non-uniform polynomial size circuits, non-uniform polynomial size symmetric circuits, I should say, and symmetric linear programs, this counting width is bounded by a constant. We have shown lower bounds. So I did this for the CFI graphs, but the same argument works for the problem XOR SAT. The counting width of the XOR SAT problem is at least square root of n by construction on toroidal grids. In fact, it can be pushed up to a linear bound by considering expander graphs instead. Okay. So now let's talk about constraint satisfaction problems. A constraint language is a finite domain and a collection of relations on D. This is entirely familiar. This is what we call a relational structure, a finite relational structure. So CSP gamma, the constraint satisfaction problem for the fixed constraint language gamma, is defined as a problem of deciding, given a set of constraints, whether it is satisfiable. What is a constraint? A constraint is a pair V, where V is a tuple of variables whose length is, let's say, A, and R is some relation from gamma of RTA. So we can think of a collection of these constraints as simply another relational structure in the same vocabulary, now one whose universe is all the variables that appear in the constraints. And the relation R is interpreted as all those tuples for which a constraint of this form is present in our problem. And then solving this constraint satisfaction problem means finding an instantiation for all the variables in this domain so that the value of this tuple of variables is in this relation, which really is the same thing as saying, if we think of this as itself a relational structure, we're looking for a homomorphism from our instance I to the fixed structure gamma, right? We think of gamma as a finite relational structure. Okay. Now, a constraint satisfaction problem is said to have bounded width. Take it as a definition. If the complement of this class is definable in data log. Now, this seems a bit strange, and I haven't told you what data log is, but I'll say it very briefly. Data log you can think of as the extension of the existential positive fragment of first order logic by a mechanism for taking least fixed points. In that sense, it's a fragment of fixed point logic, which is the what we're really interested in. And it's in some sense the existential positive fragment of fixed point logic, which means in particular that in data log you can only define class of structures that are closed under homomorphisms. Now, the way we've defined CSP gamma, the complement of a constraint satisfaction problem is naturally closed under homomorphisms, right? Because if you have a structure in the complement, it means it doesn't map homomorphically to gamma. So anything to which it does map homomorphically cannot itself map to gamma. Okay. So the complement of a CSP gamma is closed under homomorphisms, and it makes sense to ask, is it definable in data log or not? If it is, we say that it is bounded width. And really this corresponds to solvability by a very natural class of algorithms called local consistency algorithms. And that's really what data log kind of expresses. Data log is in some sense looking for inconsistency or unsatisfiability of a constraint satisfaction problem by a constraint propagation, which is what local consistency does, sort of greedy constraint propagation. And if that is sufficient to determine whether an instance is satisfiable, then CSP gamma is said to have bounded width, right? So this is a property of the finite structure gamma that does whether or not CSP gamma has bounded width. Okay, this briefly tells you what these constraint propagation or local consistency algorithms are. They construct assignments to the variables and check for k variables at a time for some fixed k and propagate. Now, data log, as I said, can be seen as a fragment of fixed point logic and therefore fixed point logic with counting, which means in particular that if CSP gamma has bounded width, then its counting width is bounded. In fact, this is where the term counting width ultimately comes from, but we've gone about it the other way. We defined counting width first. Okay, so if CSP gamma has bounded width, it has bounded counting width. In fact, that's an if and only if. It turns out that if CSP gamma is not definable in data log, then the counting width is unbounded. Now note, in general, FPC is a much more expressive language than data log. I mean, I've already told you data log is like, there are first order definable properties not expressible in data log because data log in particular is confined to homomorphism closed properties. FPC is much richer. But what this tells us is that as far as constraint satisfaction problems is concerned, FPC is the same as data log. It can't express any more. And in not just FPC, anything of any constraint satisfaction problem which has bounded counting width is data log definable. Okay, I should say, whenever I say CSP gamma is definable in data log, I mean its complement is definable in data log. But I'll use this shorthand. I say this follows by results of Atsarios, Bulatov, and myself, and Barto and Kozik. Really, it's a combination of two results. Barto and Kozik show a sort of sufficient algebraic condition for this constraint satisfaction problem to be of bounded width, and we showed that in the absence of these conditions, you can reduce, for example, XOR SAT to CSP gamma by means of definable reductions, so reductions that themselves are in data log. And that means in particular that when these conditions fail, the CSP gamma has unbounded counting width because this thing, XOR SAT, has counting width. In fact, these reductions can be made linear, so we get this sort of very sharp dichotomy, if you will, that if CSP gamma is not a bounded width, then it has at least linear counting width. So the counting width of any constraint satisfaction problem is either bounded above by a constant or bounded below by a linear function. You don't get anything in between. And it's worth comparing this with, for example, the Bulatov-Zhuk dichotomy theorem. This is a sort of major theorem in theoretical computer science, proved in 2017, settling the 20-year old conjecture of Feder and Vardy, which had motivated a huge amount of research. The dichotomy theorem says that for every gamma, either CSP gamma is in polynomial time or it is NP complete. Again, it's dichotomy because it tells you that there's nothing in between, nothing intermediate between polynomial time and NP complete, even if P is different from NP. We can also state the definability dichotomy, which is implicit in the previous slide, so this is an older result in some sense. It says that for every gamma, either its counting width is constant, in which case CSP gamma is already definable in data log, or the counting width is bounded below by a linear function, and then CSP gamma is not definable in FPC even. In particular, all this is included in the first class, and all NP-complete CSP gammas are included in the second class. They're provably not FPC. They probably have linear bounded width. But this dichotomy is not the same as that in the sense there are polynomial time problems which fall into the second category over here. For example, XOR SAT. XOR SAT can be expressed as a constraint satisfaction problem. I'll leave that bit as an exercise. Why is this a constraint satisfaction problem? Okay, now I want to talk a little bit about optimization. Suppose we are given a constraint satisfaction problem, and we're given an instance, which is a collection of constraints, and rather than determining whether it's satisfiable or not, we want to know what is the maximum number of constraints that can be satisfied. So even if it's unsatisfiable, we want to satisfy as many constraints as possible simultaneously. Again, we're not going to look for the actual satisfying assignment, just determining the maximum. This is the sort of thing that we can do in counting logics, and we can do symmetrically. So here again, we have a dichotomy, an interesting one by Topper and Givney, who showed that as long as this constraint satisfaction problem is a bounded width, then the maximization problem is solvable in polynomial time by its basic linear programming relaxation. But if it's not of bounded width, the problem is NP-hard. And an example, interesting example here is now max XOR SAT. So XOR SAT, the feasibility problem, deciding whether XOR SAT is satisfiable, is polynomial time. But because this is of unbounded width, the maximization problem turns out to be hard. Okay, it's NP-hard. So what do I mean by the basic linear programming relaxation? So suppose we have an instance of max CSP gamma, so a collection of constraints. We turn it into a linear program as follows. So we have our set of variables. The domain D of gamma is fixed, and we have constraints which are tuples of variables from V and a relation R on the domain D. So we turn this into the following linear program. So for each constraint C and each D in the relation R on gamma, we have an indicator variable lambda CD to say that C maps to D. Okay, you take the sum of our overall constraints of this. This sort of tells you the number of constraints you're satisfying. So this is what you're trying to maximize. And now these constraints sort of tell you that your they're basic consistency requirements. So this tells you that every variable is being mapped to exactly one element of the domain, if the variable xi is mapped to A, for every xi occurring in the constraint C, then then the constraint C is mapped to the tuple of elements D. So we have in this linear program, essentially the variables lambda and mu are the variables of our linear program. And think of mu xia as the indicator variable saying that the variable xi is mapped to A, and lambda cd as the indicator variable that the constraint C is satisfied by the tuple of elements D. Now it is as defined here. This really defines as a linear program whose, if it 0-1 solutions, 0-1 solutions correspond exactly to assignments of values in the domain D to the variables, and maximizing this overall 0-1 solutions would give you exactly the value of max CSP. But of course, that's an integer linear programming problem. So if we just add the constraints, essentially, let's say that lambda mu are all between 0 and 1, that's a 1, then we get we get a linear programming relaxation. We can optimize for that, and that gives us, as it were, an approximation to max CSP. Now, once you have a linear programming what we call the basic relaxation of our constraint satisfaction problem, a solution to it doesn't give us, as I said, an exact solution. It'll give us what's called a fractional solution, right? These lambdas and mu's in our optimum will have values possibly strictly between 0 and 1. So that's not sort of a meaningful solution. It's not a meaningful assignment of values to the variables. But it allows us to estimate the actual optimum value. And it is, in some sense, usually an upper bound, because we've relaxed it, so we're allowing solutions which are not integer solutions, So we're achieving a maximum which may not be achievable by integer solutions. We can get a better approximation by tightening the linear program, by adding additional constraints. Okay, so what we're after is we're after the integer points in this. So in the polytope defined by our linear programming relaxation, what we're really after is the convex hull of the integer points. That, if we could optimize over that, we would get exactly what we want. Instead, we're getting something which includes the convex hull, and we can tighten it with additional constraints, and there are systematic ways of doing this called lift and project programs. General idea is that for the variables in your original program, you add, for tuples of variables, I should say, in your original program, you add new variables to denote the product. Of course, you can't say that this is the product because that's not a linear constraint. But you add linear or sometimes semi-definite constraints to force this meaning. And increasing the value of t gives you increasing hierarchies of tighter and tighter approximations of the program you're trying to maximize over, optimize over. As I said, there are systematic ways of doing it, one defined by Schererli and Adams. There's what's called the Lowas-Shriver, and there is a Lasserre hierarchy. I'm not going to give you formal definitions. For our purposes, we'll talk about the Lasserre hierarchy because it's in some sense the strongest. That is, for the purpose of these constraint satisfaction problems, the Tth Lasserre tightening or lift gives us a tighter approximation than either of the two others. Okay, so that's the sense in which it's the strongest. Okay, so what do we have? We have a polytope defined by a linear program, ax equals b. Now, t will vary from 1 up to b, the number of variables. And if we have a vector y so each of these is, as it were, a tightening of this polytope. It's a further restriction. K star is the thing we're interested in, which is the convex hull of the integer points inside K. This is contained in all of these. Okay, ignore the pi here for a moment. As you increase the degree of the Lasserre hierarchy, you get tighter and tighter restrictions. And at the end, again, ignoring the pi, if you take t all the way up to the size of v, you get k star, which is exactly the convex hull of the integer points. So what does all this have to do with FPC? What we were able to show in a paper of mine with Pengming Wang is for each gamma and t, you can define an FPC interpretation which takes a CSP instance I, and it defines within it the linear program, which is the tth level of the Lasserre hierarchy over BLPI. I should actually say the Lasserre hierarchy is not linear programs, it's semi-definite programs, but yes, I should have said that. It gives a semi-definite program. And the FPC implementation of the ellipsoid method, which we saw earlier, extends to semi-definite program, subject to some technical conditions, which it turns out we can satisfy in this case. So it follows that if the tth level of the Lasserre hierarchy actually solves max CSP, in other words, it gives you exactly the convex hull of the integer points in this basic linear programming relaxation. So it gives you the exact value of max CSP. Then t is bounded below by the counting width of gamma. Why? Because if you can solve max CSP gamma, right, by this implementation, by this implementation of the ellipsoid method, combined with this interpretation, we can get an FPC formula that solves max CSP gamma. this interpretation is linear. So the number of variables needed in our FBC formula is linear in T. So if this counting width of CSP gamma is, for instance, linear, then it follows that T must also be bounded below by a linear function. So if CSP gamma is not a bounded width, then you need a linear number of levels of the Lassère hierarchy to obtain the convex hull of the integer solutions. Again, either a constant number will do, or you need a linear number of levels of the Lassère hierarchy. You get this sort of strong dichotomy. Okay, that's sort of the first application. I guess what I wanted to stress is that the Lassère hierarchy of semi-definite programs is a widely used method for solving optimizations, constraint optimization problems. And we get solid, concrete lower bounds on the number of levels you need based purely on this notion of counting width. And what we're really saying here is that these semi-definite programming methods inherently are symmetric algorithms. That's what this part is saying. They are symmetric algorithms, and therefore our lower bounds for symmetric algorithms apply to them. We'll take a brief pause and return and look at some more general hardness of approximation results for CSPs and other problems.